Very good morning, one and all. Another important topic that we are going to discuss today is cerebellum. Learning objectives will be at the end of this session, you will be able to understand divisions and various functions of cerebellum, connections of cerebellum, arrangement and functions of the cells in different layers of the cerebellum, internal neuronal arrangement and their function within the cerebellum, influence of deep cerebellar nuclei with descending pathways, cerebellar disorders and functions of the cell. Let us start. It is also called as the silent area of the brain, as it is when stimulated electrically does not cause any conscious sensation and rarely cause any motor movement. It remains silent and therefore may be called as silent area of the brain. Its removal causes highly abnormal body movements, almost total lack of coordination of rapid muscular activities like talking, running, typing, and so on. It plays major role in timing the motor activities, in rapid onset and smooth progression of muscle, controls intensity of muscle contraction during movements, and immediate interplay between the agonist and the antagonist muscle. If we see its location, it is located in the posterior occipital fossa and connected on each side to brain stem by three cerebellar peduncles: inferior, middle, and superior. By inferior cerebellar peduncle, it is connected to medulla, as we can see in the diagram also. By middle cerebellar peduncle, it is connected to pons, and by superior cerebellar peduncle, it is connected to medulla. It weighs about 10% and surface area is about 75% of the cerebral cortex. There are three divisions or lobes of the cerebellum: anatomical, phylogenetic, and functional. Let us see one by one. Anatomical divisions. It has two parts, two lateral cerebellar hemispheres. Can we see here in the diagram? There are two cerebellar hemispheres. They are laterally placed, and small medial vermis, which has got two parts: flocculonodular lobe, this is the flocculonodular lobe, and corpus cerebellum, which has got anterior part and the posterior part. So this is flocculonodular lobe and this is corpus. Anterior lobe of the corpus cerebellum is having these parts: lingula, lobulus centralis, and the culmen. Lingula, lobulus centralis, and the culmen. Whereas the posterior lobe has got lateral part which contain ensiform and paramedian lateral lobules. This is the ensiform and the paramedian lateral lobule. Median and paramedian parts containing lobulus simplex, declive, tuber, pyramus, uvula, and the parafluvia. This particular part. Coming on to phylogenetic division based on the development of the lobes at different times during the evolution. Archicerebellum. This particular part, archicerebellum, it is first to develop and includes flocculonodular lobe. This is a nodule and these are the floccules. Paliocerebellum, this particular part, evolved next to the archicerebellum and includes entire anterior lobe and lobulus simplex of the posterior lobe, as we can see in the diagram also. Neocerebellum, it is last to evolve and includes remaining part of the posterior lobe. Coming on to the functional division of the cerebellum. It depends on connection they made with other components of the motor system, and accordingly they are vestibulocerebellum. It is also called archicerebellum or the flocculonodular lobe. Has got connection with the vestibular nuclei or the vestibular apparatus, as we can see here in the diagram. What is the function it is carrying out? It concerned with the control of body posture and equilibrium as well as the eyeball movements. Spinocerebellum, this particular part. Paliocerebellum or entire anterior lobe and parts of posterior lobe includes the spinocerebellum. Receive information from the spinal cord, proprioceptive inputs from the body, and copy of motor plan from the motor body. And thereby, it helps controlling the skilled movements as well as controlling the. Next, neocerebellum, which is also called cerebrocerebellum. It is the remaining parts of the posterior lobe comprising the neocerebellum. It receives information from cerebral cortex and the pons. It is mainly responsible, or it is mainly playing important role in planning and programming of the. This diagram shows us functional division, spinocerebellum, vestibulocerebellum, and neocerebellum along with their functions and the parts that are in. Functional unit of the cerebellar cortex. Cerebellum has got about 30 million functional units, which centers on a single very large Purkinje cell, as we can see in the Purkinje cell, and on a corresponding deep nuclear cell. This is a deep nuclear cell. Cerebellar cortex has got three major layers: molecular layer, Purkinje cell layer, and the granular cell. Beneath this layer, in the center of the cerebellar mass, there are located deep cerebellar nuclei. These are the deep cerebellar nuclei which send output signal to other parts of the nervous system. Deep cerebellar nuclei are of four types. Nucleus fastigius, as we can see here, fastigial nucleus, located in deep vermal portion of the cerebellum. Vermal portion of the spinocerebellum project to it. Nucleus globosus and nucleus emboliformis. Globus nucleus and emboliform nucleus, together they are called nucleus interpolliceus. Paravermal portion of the spinocerebellum project to it. Then nucleus dentatus. Nucleus dentatus or the dentate, as we can see here. Located in the hemispheric portion of the cerebellum, receive inputs from neocerebellum as it has a teeth-like serrated morphology, hence the name dentate. Coming on to the neuronal circuit of the functional unit. Cerebellum has about 30 million functional unit, that is Purkinje cell and the deep nuclear cell, as we can see here in the cerebellar cortical layers. Purkinje cell and the deep nuclear cell. Output from the functional unit is from a deep nuclear cell. This particular output is ultimately coming from the deep nuclear cell. This cell is continually under both facilitatory as well as inhibitory influence. Basket cell and stellate cell are other inhibitory cells located in the molecular layer of the cerebellar cortex. As we can see here, basket cell and the stellate cell, which are located in the molecular layer, which is the superficial layer of the cerebellum, are lying among the small parallel fibers and stimulated by them. In turn, they send their axon at right angles across the parallel fiber, as we can see here, cause lateral inhibition lateral inhibition of adjacent Purkinje cells to sharpen their signal. What the lateral inhibition role is in the sensory system, that we have already described while learning about the various aspects of the sensory system. Then there is a phenomenon called turn on, turn off, and turn off, turn on output signals from the deep cerebellum at the onset of movement. That means when any of the movement is initiated, cerebellum is providing rapid turn-on signals for the agonist muscle so that the movement will be brought about, and simultaneous reciprocal turn-off signals are going to the antagonist muscle so that there will be no any reverse action from the antagonist muscle in order to stop or obstruct that particular desired movement. Upon approaching to the termination of the movement, when the movement is about to terminate or end, cerebellum is responsible for timing and executing turn-off signal to the agonist and turn-on signal to the antagonist muscle so that the movement can be smoothly turned. After being discussing various functional division, anatomical division, and the phylogenetic division, now it's a time to study about connections of the cerebellum. This particular chart is showing us cerebellar inputs via the different fiber system, which include climbing fiber, mosey fibers, and the other fiber systems. Cerebellar outputs from the vestibulocerebellum. it directly projects to the vestibular nuclei. These are the vestibular nuclei, and this is the vestibular cerebellar output, which is directly projecting to the vestibular nuclei without any relay in deep cerebellar nuclei. Thus, it directly controls the activity of vestibulospinal tract. From spinocerebellum, vermal portion project to fastigious nucleus. This is the vermal portion. It is projecting to fastigious nucleus, which in turn is projecting to pontine reticular formation and the vestibular nuclei in the brainstem. Pontine reticular formation and vestibular nuclei in the brainstem. Thus, we can say that it controls the activity of pontine reticulospinal and vestibulospinal tract. Both these tracts activity will be controlled by the vermal. Paravermal portion project to interpogicious nucleus. This is the interpogicious nucleus. This is the paravermal portion. It is projecting to the nucleus, which in turn is projecting to radius, and thereby it controls the activity of rubrospinal. From cerebrocerebellum, cerebellar hemisphere project to dentate nucleus. This is the dentate nucleus where the cerebrocerebellum is projecting, which in turn is projecting to motor cortex via the thalamus. Thus, it controls the activity of this particular descending tract, that is pyramidal tract or the cortical spine. After this, it's now time to discuss about various internal connections of the cerebellum. Internal connections of the cerebellum. Facilitatory influences arises from two sets of fiber, climbing fiber, as we can see here, and the Mosey fiber that enter the cerebellum from the brain or the periphery. Inhibitory influence arises entirely from the Purkinje cell, which are located in the cerebellar cortex. This is the Purkinje cell, which is giving rise to inhibitory influences on the deep cerebellar nuclei. Climbing fibers. It originates from inferior olive of the medulla, and ratio of one climbing fiber is about 5 to 10 Purkinje cell. That means for 5 to 10 Purkinje cells, there is the presence of one climbing. Climbing fiber send branches to several deep nuclear cell, then continues all the way to the outer layers of the cerebellar cortex. It is sending branches to the deep nuclear cell of the cerebellum, and ultimately other branches are going to the cerebellar cortex, where it makes about 300 synapses with each Purkinje cell. Climbing fiber is distinguished by the fact that it is a single impulse. Its single impulse always causes a single prolonged up to 1 second peculiar type of action potential in Purkinje cell with which it is connecting. Beginning with a strong spike, this one, followed by a trail of weakening secondary spike, which are called the complex spike. After climbing fiber, another set of fiber is a Mosey fiber enter the cerebellum from multiple sources like higher brain, brainstem, and the spinal cord. They also send collateral to excite deep nucleus cells, as we can see. They have got the facilitative influence on the deep nucleus cells. They then proceed to granule cell layer, where they synapse with many granule cell. In turn, granule cell sends small axon up to the molecular. There are about 500 to 1000 granule cell for each Purkinje cell, as we can see. As axons of granule cell in two molecular layer divide into two branches, there exist millions of parallel nerve fibers of the granule cell. This parallel nerve fibers, as we can see. Mosey fiber input to the Purkinje cell is quite different from that of the climbing fiber, as synaptic connections are weak in case of the Mosey fiber as compared to the climbing fiber. And therefore, large number of Mosey fiber must be stimulated simultaneously in order to stimulate the Purkinje. In Mosey fiber, single impulse always causes a single weak and brief action potential in Purkinje cell. That is a simple spike rather than prolonged complex action potential caused by climbing fiber unit, as we have already seen, which is called complex. This particular part. Excitatory output from the cerebellum. Purkinje and the deep nuclear cell fire continuously under normal resting condition. Purkinje cell is giving rise to 50 to 100 action potential per second, whereas deep nuclear cell much higher rates as compared to the Purkinje cell. Input from both climbing fiber and Mosey fiber directly facilitate deep nucleus cell. As we can see, this is the input from Mosey fiber, this is the input from climbing fiber. Both has got the facilitatory input on the deep nucleus cells of the cerebellum. Input from Purkinje cell being GABAergic has got the inhibitory influence. This is a Purkinje cell, has got inhibitory. Normally, balance between these two effects is strongly in favor of facilitation, so that under resting condition, output from the deep nucleus cell of the cerebellum is always excitatory. After being considering various connections parts of the cerebellum, now it's a time to discuss various functions of the cerebellum. The first among which is control of body posture and equilibrium. Vestibulocerebellum is playing important role in this particular function, controlling the balance between contraction of agonist and the antagonist sets of muscle of the spine, of the hips, shoulders during rapid changes in the body. Signal from periphery tells the brain how rapidly, that is rate of the movement, and in which direction different parts of the body are moving, that is direction of the movement. From the rates and directions, vestibulocerebellum calculate in advance that where different parts will be going during the next few milliseconds. This feedback is provided anticipatory correction for the postural motor signal necessary for maintaining equilibrium even during the extremely rapid motion. Next function is control of muscle tone and stretch reflex. Cerebellum through its output from fastigial nucleus influences activity of major descending medial system pathways, especially of vestibulospinal tract, which is involved in control of alpha motor neuron activity, whereas reticulospinal tract, which controls the gamma motor neuron activity. And we have already studied what is the role of gamma motor neuron and alpha motor neuron in the contraction of. So, cerebellum is one of the major sites for the alpha gamma co-linkage and thereby control muscle tone as well as the stretch. Coordination of movement. Spinocerebellum is receiving proprioceptive as well as other sensory inputs like rate of the movement, range of the movement, force, direction, and time of the movement from all parts of the body. Through the spinal cord, it also receives input from the motor cortex, where the motor planning is carried out. By comparing the plan of the movement with the performance of the movement, it smoothens and coordinates voluntary as well as involuntary movement. Cerebellum doesn't initiate, rather it plays very important role in coordination of the movements which are initiated by the motor. Next function is prevention of overshoot of the movements or to damp the movement. Almost all body movements are pendular and therefore they develop momentum when the movement is going on. For example, when the arm is moved while walking, momentum develops and momentum must be overcome before the movement can be stopped. To the momentum, all pendular movements have tendency to overshoot. If cerebellum is intact, appropriate, learned, and subconscious signals stop the movement precisely at the intended point and thereby damping the movement, which prevent either overshoot or the tremors. The tremors which are of two varieties, action tremors and the intent. Next function is control of ballistic movements. Movement is pre-planned and set into motion to go to a specific distance and then to stop. For example, saccadic movements of the eyes. Eyes jump from one position to the next when reading a book or looking at successive points along the road as the person is moving in a fast moving car. In absence of the cerebellum, movements are slow to develop and force developed is weak, and movements are slow to turn often going beyond the intended. So, in absence of cerebellum, motor cortex has to think extra hard to turn the ballistic movement on, and again has to think hard and take extra time to turn these movements. Thus, the automatism of ballistic movements is lost if the cerebellum is not playing its role. Planning of sequential movements. Actually, the planning of sequential movement is beginning in the premotor area, primary sensory, and the sensory association area of the cerebral cortex, from where this plan is transmitted reciprocally to the neocerebellum. Reciprocally in the sense to and fro the neocerebellum. This provides appropriate motor signal leading to transition from one sequence of movement to the next. Next function is timing of sequential movements. In absence of neocerebellum, one loses the subconscious ability to predict ahead of the time that how far different parts of body will move in a given time. This makes the person unable to determine when the next sequential movement needs to begin, and thereby ultimately causes failure of smooth progression of the function of the cerebellum is extramotor predictive. Neocerebellum also is playing very important role in timing the events rather than timing the movements of the body. For example, when a person predicts from a changing visual scene or changing intensities of the sound that how rapidly he or she is approaching to the particular object. Next is functions of pyramus, uvula, and paraflocculus part of the cerebellum. Pyramus, it is concerned with the eyeball movement as its stimulation is causing upward and ipsilateral eyeball movement, and it is also concerned with judgment of the distance. Uvula has vestibular function as its removal in animal causes disturbance in equilibrium. Paraflocculus, it is rudimentary in case of human beings, but is highly developed in the aquatic diving animals, showing that it plays an important role in extensive reflex adjustments necessary for. Then, role of cerebellum in learning. Cerebellum is concerned with the learned adjustments, that is making coordination easier when a given task is being performed over and over repeatedly. After being thoroughly going through the various functions of the cerebellum, in case there is any lesion, any abnormality of the cerebellum, what particular kind of features or clinical features it is going to give rise, that we need to discuss now. Destruction of small portion of the lateral cerebellar cortex rarely cause detectable abnormalities in motor function, as remaining portion of the motor control system are capable of compensating. To cause serious and continuing dysfunction of the cerebellum, the cerebellar lesion usually must involve one or more deep cerebellar nuclei. Let us see the various conditions: dysmetria and ataxia. What is dysmetria? Dys is a wrong, metria is a length or a meter. A movement characterized by undershoot or overshoot of intended position with the hand, arm, leg, or eye. It is sometimes described as an inability to judge the distance or scale. Hypermetria or hypometria refer respectively to overshooting and undershooting the intended position. Ataxia, as we have mentioned that one of the important functions of the cerebellum is to coordinate various movements. Whenever there is absence of coordination of movements, the condition is called as ataxia. Ataxia could be of two types: sensory ataxia and motor ataxia. Sensory ataxia is because of the lesion in the dorsal column pathway, whereas motor ataxia whenever there is lesion in the cerebellum itself, and hence motor ataxia is also called as the cerebellar ataxia. Thus, coordination of movement is an integrated activity of sensory as well as motor system. Pass pointing. In absence of cerebellum, a person ordinarily moves the hand or some other moving part of the body considerably beyond the point of intention, and therefore pass pointing is actually a manifestation of this. Failure of progression. There are three conditions here: dysdiadochokinesia, diadochokinesia, and adiadochokinesia. What is diadochokinesia? Ability to perform rapid alternate movements, that is alternate pronation and supination of the forearm this way. Rapid and alternate supination and pronation of the forearm. When the motor control system fails to predict where different parts of body will be at a given time, it loses perception of the parts during the rapid motor movement and leads to dysdiadochokinesia. That is, succeeding movement may begin too early or too much late, so no orderly progression of the movement can occur. That means there is possibility that the person is able to perform rapid and alternate supination and pronation, but there is too much difficulty to begin with the movement, and once it is begun, there is too much difficulty to stop the movement, and hence the condition is diadochokinesia. Adiadochokinesia, that is, there is total failure of doing the rapid alternate movements. These are three: failure of progression in talking. because of the formation of words depends on rapid and orderly succession of the individual muscles movements in the larynx, mouth, and respiratory system. Lack of coordination among these all structure and inability to adjust advance either intensity of sound or duration of its successive sound, it causes jumbled vocalization with some syllables coming loudly, some weakly, and some held for a longer interval, whereas some held for a short, which result in speech that is often unintelligible, and this type of speech will be labeled as dysarthria. Intention tremor, a person without cerebellum performs a voluntary act. The movements tend to oscillate, especially when they approach the intended mark. First overshooting the mark, then vibrating back and forth several times before settling on the mark. And therefore, it is said to be the intention or the action tremor. That is why it is called action or the intention tremor, because when the person is having intention to hold something, and while beginning with the activity, that is holding that particular object, the intention is to hold that particular object and the tremor will start, and therefore it is called intention or the action. It results from cerebellar overshooting and failure of damping the motor movements by the cerebellum. Cerebellar nystagmus or tremor of the eyeball. It usually occurs when one attempts to fixate eyes on a scene to one side of the head. This off-center type of fixation results in rapid, tremulous movements of the eyes rather than steady fixation. It is one of the manifestation of failure of damping by the cerebellum. It is another manifestation of failure of damping by the cerebellum. It is also associated with loss of equilibrium because of dysfunction of the pathways through the flocculonodular lobe of the cerebellum from the semicircular. Last is hypotonia. Loss of deep cerebellar nuclei like dentate and interpostitious causes decreased tone of the peripheral body muscle on side of the cerebellar lesion, as normally the deep cerebellar nuclei send facilitate the signals to the motor cortex and brainstem motor. Yeah. Thank you so much.